Okay, so here we are on February 7th in MTH 126, and this lecture is about binomial probability. I want to remind you of some things we've already talked about just to set the stage, but you should know that the Cooper textbook Chapter 6 is about binomial probability, and I urge you to read that. Likewise, the Triola online textbook, Chapter 5, Sections 2, 3, and 4 are very good things to read. We've had the idea of a population and a random variable, which takes measurements on members of the population. Call it X. It has values on a number line, and we've had the concept of the population mean, mu, the population standard deviation, sigma. We've also had the idea that if you take a sample of size n, it has a standard deviation for the sample of little s, and the sample mean x bar. We've also had the idea of more than one random variable on the same population, and we've had the idea of two different populations with the same measurement, like that. Today we're going to introduce a simpler and a more complicated thing at the same time, and I'm going to illustrate it with a simulation in Excel about coin flipping. Now, a coin normally looks like this, and it has a heads, it has a tail side, and it has a thickness. In this course, we don't talk about real coins. We talk about an ideal coin, which has a probability P, the probability of heads. A perfectly fair coin has a probability of heads of 0.5 and a probability of tails of 1 minus P, which is the probability of tails, and so that P plus 1 minus P equals 1. Q is usually used to denote 1 minus P. Notice that I have not included in P or Q the possibility that the coin lands on edge, which has a very, very tiny probability, and that's why I'm saying I'm talking about an ideal coin. We'll take a 0 for the probability of landing on edge. So we're talking about P coins. Now, if you have a population of coins, all P coins, the random variable that you might use to represent the idea of heads or tails, we'll call it little b. You could let 0 stand for tails and 1 stand for heads. You have a whole bunch of coins. And you imagine that they're all flipped, and you take one coin at a time that you flipped and take a look and see if it's heads or tails. The story gets, there's nothing more to say about that. I mean, a single coin at a time is the simplest binomial random variable you could possibly have. But suppose we take, let's say, 13 coins at a time. Let me see if I can get 13 coins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And do that over and over again. But think of those 13 coins. Let me double check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. Think of that sample of size 13 as being a single member of a new population whose members are samples of size 13 from the original population of coins. Okay, so this is a sample. We can even call it a 13 sample. So we're talking about a 13 sample of P coins. Now you have a more interesting random variable, namely, we'll call it capital B, namely, how many of those 13 P coins came up heads in this particular sample of size 13. Now there are various possibilities. You could have all tails, so there's 0 heads, 1 head, 2 heads, 3 heads, and so forth, up to 13 heads. So there are 14 possible values for this random variable capital B. That's an interesting random variable. And the main question is, what is the probability, I'll abbreviate that, what is the probability of, I don't know, let's say 5 heads in 13 tosses of a P coin? That is the basic question of this whole chapter. It won't always look like it's talking about coins, because it could be talking about anything where you have 2 possible values of a random variable, whether it's red or black, or yes or no, asking, I don't know, students whether they went to class today, and so forth. There's all kinds of binary questions that you could ask, but they can all be translated into a question about a coin coming up heads or tails. Let's stop here and see if we have a finished chunk